Hello, welcome back. In this video we will discuss the hysteresis in magnetism. A typical property of ferromagnetic material is hysteresis. So it is essentially a property of a ferromagnetic material. Hysteresis may be defined as the lag in the change of magnetization behind variations of the magnetic field. It is defined as the lag in the changes of magnetization behind variations of the magnetic field. Because of hysteresis, the magnetization of a ferromagnetic material depends not only on the strength of the magnetic field that produces the magnetization and also on the magnetization history of the material. In fact, it explains the magnetization of a unmagnetized ferromagnetic material. The magnetization depends on two factors. One is the applied magnetic field intensity and the history of magnetization. So hysteresis essentially gives us information about these two. One is how the unmagnetized ferromagnetic material can be magnetized in an external magnetic field, and also how the magnetization is going to depend on the history of magnetization. If an initially unmagnetized specimen of a ferromagnetic material is subjected to an increase in the magnetic field or a decrease in the magnetic field, then one can notice the hysteresis loop. The magnetic field induction B varies as a function of H along a closed loop called the hysteresis loop. It is essentially a loop. What loop is this? If an initially unmagnetized specimen of a ferromagnetic material is subjected to increase or decrease of the magnetic field, the magnetic field induction B varies as a function of the H along this loop, which is called as the hysteresis loop. If you have an unmagnetized ferromagnetic material and if you keep in some external magnetic field whose strength is H, then you have a magnetic field induction B within the ferromagnetic material, and the magnetization will follow a loop that is called as the hysteresis. Now we shall discuss the hysteresis loop in detail. This is called the hysteresis loop. It is also called as the BH loop or BH curve, and these BH curves or BH loops can be seen in ferromagnetic materials because it is a special property of the ferromagnetic materials. So if you take an unmagnetized ferromagnetic material and place it in an external magnetic field, then the magnetic field induction B in the ferromagnetic material increases slowly. It starts from a 0. This 0 corresponds that there is no magnetic field induction within the ferromagnetic material since it is an unmagnetized ferromagnetic material. Once the external magnetic field intensity H is started increasing, you notice that it slowly increases and it reaches a value called as the saturation induction. So from O it begins, as H is increased, the field B begins to increase slowly. When H is increased, the field B increases slowly, then more rapidly somewhere here it increases more rapidly here and becomes independent of H. After reaching this value, even if you increase the H value, you do not see any variations in the B field, which indicates that we have reached a saturation flux density. So BS is called as the saturation flux density, and the corresponding magnetization is the saturation magnetization. So when you have a saturation flux density, you will have a saturation magnetization. It is called saturation magnetization. It is represented with an MS. After reaching the saturation flux density, if H is now decreased, B also decreases. you see B also decreases. Initially we have started from 0, or let us say O, that is the origin, and we have reached a point A. The initial path is O to A. If H is now decreased, you see that the B decreases slowly, but the decrement is not along the path OA, but it traces a new path, that is AB. Instead of the original path AO, now it takes the path AB. Thus, B lags behind H. And when H becomes 0, it reaches a value B here, which means the flux density is not 0. The applied magnetic field intensity is 0. And this is what is called as the retentivity or the residual magnetism. So when H becomes 0, B does not become 0 and will have a value equal to B, or the value is OB. This magnetic flux density remaining in the materials is called the residual magnetism. It indicates that the material remains magnetized even in the absence of the external applied magnetic field H. So the power of retaining the magnetism is called retentivity or remanence. It is the power of retaining magnetism. So retentivity or remanence is the power of retaining the magnetism in a ferromagnetic material even when the applied magnetic field intensity H is 0. The retentivity of a material is a measure of the magnetic flux density remaining in the material when the magnetic field is removed. Now, if the magnetic field increased in the reverse direction, the value of B is decreased. H is increased in reverse direction. Look at the curve here. When the magnetic field is increased in the negative direction, the B field slowly decreasing. Now it is going to follow the path BC, and at C it becomes 0. At point C, B field is 0, and this becomes 0 when H attains a value that is equal to OC. It means that to reduce magnetic induction within the material to 0, a field of magnitude Hc is required. So to make the B field again equal to 0, a magnetic field intensity of Hc is required in the opposite direction. And here Hc is called as the coercivity or the coercive force. So initially magnetic flux density in the material is 0. We are increasing so that it reaches a saturation. From there we are reducing the magnetic field in the positive direction. So we are making it to 0. When the magnetic field is made 0, we will have a flux density which is not equal to 0, that is equal to OB. So much of flux density is present in the ferromagnetic material. And this quantity is called as retentivity or the remanence. And after reaching the value for H is equal to 0, you change the direction of the H field and start increasing in the negative direction. Upon increasing in the negative direction, you find that the magnetization decreases and the flux density also decreases within the material and eventually becomes 0 for a magnetic field intensity Hc on the opposite direction. This field is called the coercivity of the material or the coercive force. Coercivity is a measure of the magnetic field strength required to destroy the residual magnetism in the material. It is a measure of the magnetic field strength that is required to destroy the residual magnetism in the material. If the field is further reduced or if the field is further increased in the negative direction, the flux density takes the path CD, and here also it reaches a saturation value. After reaching the saturation value, you decrease the field strength in the negative direction. Then you see that slowly it decreases and reaches a value E here, OE, the magnitude will be OE. And here when it reaches E, we have a remnant magnetism or retentivity OE on the negative direction. If you increase the magnetic field intensity from the negative direction to 0, you find that the flux density B is not 0 but it is OE, and this amount of flux density is called as the retentivity on the negative direction or the remnants in the negative direction. Upon increasing again the magnetic field intensity in the positive direction, the flux density decreases, eventually it becomes 0 here. The flux density becomes 0 for the positive coercivity. Upon increasing again the magnetic field intensity in the positive direction, that is F to A, the curve traces. It is not from O to A now. Now it is D, E, F, A, B, C, D, E, F, A. Like that it goes. It will not come back to O. The closed loop is also called as the cycle of magnetization in ferromagnetic materials. In this video we have seen what is hysteresis. We have said that it is a property of ferromagnetic materials and it is defined as the lag in the changes of magnetization behind the variations of the magnetic field. Hysteresis essentially gives us two important aspects of the ferromagnetic materials. It gives us the magnetization increases with respect to the applied magnetic field intensity, and also the magnetization depends on the history of magnetization. The hysteresis loop is also called as a BH curve or BH loop. It looks like this. When a unmagnetized ferromagnetic specimen is kept in an external magnetic field intensity H, which is equal to 0, then B also is 0. When the magnetic field intensity H is slowly increased, the magnetic flux density increases slowly and further it increases rapidly. It reaches a value beyond which, even if there is a change in the external applied magnetic field intensity, no significant change in the B field can be seen. The B field is called as saturation flux density and the corresponding magnetization is called as saturation magnetization. From there, if you reduce the applied magnetic field intensity, instead of taking AO path, the magnetic flux density takes the path AB and it reaches B for a value of H, which is equal to 0. When H is equal to 0, the B field will be equal to small b. And this is what is called as retentivity or remanence. From there, if you increase the magnetic field intensity in the opposite direction, you will reach a point C for which the magnetization is 0 and the flux density also is 0 in the ferromagnetic sample. The required magnetic field intensity is called as coercivity or the coercive force. Upon decreasing further, we reach a saturation at D and again retentivity at E and coercivity at F and again saturation. So the magnetization always changes along this loop. The changes in the magnetization with respect to the changes in the applied magnetic field will follow this loop, which is called as the hysteresis loop. Thank you.